Hello everybody and welcome back. So it's the end of week 3 and we've spent the week learning some advanced vex, all of the powerful things that it can do, some much more advanced techniques and syntax and things. And I would like to now show you a practical example just to help you sort of reiterate everything we've learned in the week, put it into practice, let you see how much of it is absorbed and try to sort of grapple with a little bit more of it so that it can really sink in. So what we're going to be talking about today, kind of a good example of how to use everything, all the arrays and blocks and the PC opens and things that we learned during the week, is creating sort of a naturally imperfect propagation. And we're going to do that on some deforming geometry just to make it even a little bit harder. So basically I've got a setup here where we have this attribute that is spreading across the geometry, but it's obviously a piece of deforming. I mean, I've just used some basic vellum to make a sort of a little cloth sim. So we have actual, deforming geometry, but then we have this attribute that is spreading, and we often use this for things like, like a burn map or a decay map, something like all of this cloth that may be actually tearing away or dissolving and disintegrating, or even just changing color, to some sort of technique where the flag changes color as it's waving around, or something like that. Okay, there's a lot of things you can do with it, but one of the problems though is that a lot of the techniques for creating propagation is just it spreads too evenly. It just sort of spreads out in a giant circle, especially if it's from a single point. So how do we get it to create these much more interesting shapes? And in fact, we could even push it a little further than this. But how do we end up with like a hole over here that hasn't quite had information spread to it? But it's not a post multiplier, because give it a little bit of time and you'll see that point eventually does get covered. So why is it spreading faster to other areas than and slower in others to create this kind of, these cool shapes? So that's what we're going to be talking about today, and we're going to use all the vex that we learned in the week to do that. So I encourage you guys, as I have in all of the previous practical lessons, to try and rebuild this as I go through it. I'm going to sort of show you what every node is doing. Try to rebuild it in your own way. Even if it's not exactly the same as mine, see if you can get the same results. There are always a million ways to do things in Houdini, so your method is not incorrect. But if you're not getting the right result, then it may need to change. But you can always ask for help. But I would encourage you trying different methods, or trying the same method. But if you get lost, don't just download this help file and use it as is. Use it as a reference, or use this video as a reference as I'm walking through it, and see if you can try and figure it out, because you will learn a lot more by doing that. Okay. I know I've said that before, but you guys, I cannot stress how much just messing around with things is actually honestly the way to learn things in Houdini. So we start with a basic grid, and I'm just pinning, I'm creating a pin group in here. So I'm just using a group expression to kind of create this pin group where my Z axis is above a certain threshold, but I'm basically grabbing the size, halving it, because it's it's sitting around the origin, and then taking that just slightly less. Basically what this equates to is me grabbing all of the points along the one edge and putting them in a group. Okay, but it's done procedurally. So if I change my grid resolution, it'll still just work. Okay, and I'm going to use that in here. So I've got some kind of animation. I'm just rotating by at frame, and I've got a sine wave on my translation. So I'm getting this kind of weird spinning technique, which obviously will only apply to the group that is pinned. Okay. And then I'm just creating vellum constraints here, and I know you can do the vellum with the just the sort of the vellum nodes without going inside of a DOP, but I I like to do this because I feel like I have more control over the actual simulation. So anyway, that's just personal preference. So in here, I'm basically just simulating the cloth, right? This tutorial is not going to be about cloth simulation. So, you know, I'm not going to go in heavy into detail. I mean, I really didn't do anything here except basically just the standard cloth simulation with a pin constraint at the top. Okay. So we just got a piece of cloth flapping around, and this is what we're going to be using to do our propagation on. Okay, so then there's all the sort of film post-process stuff, and then I'm caching my cloth sim just so that it's a lot easier to kind of read in this rather than having to simulate live. Okay, so this side of it, nothing fancy, nothing special. Okay, just standard vellum. Here is where the work is going to happen. So yeah, you see there, it's now showing my pin group. So I'm time shifting this to make sure that it's frozen. Obviously there wasn't any animation on it already, but this is just good practice, because if you do then import a piece of geometry that does have some animation, you don't want it to mess up your whole system. So I do freeze whenever I'm going to do something like this. Then I'm scattering loads of points on the surface, because what we're going to do, we're going to need points to spread that data. You don't want to have to subdivide this mesh in order to, because we're storing data at point level. So if we're only storing at point level, then we're going to store some data here, and we're storing some data there, and everything in between needs to get interpolated. And generally, it's just a straight up linear interpolation, which is not a good result. It looks very blocky. Okay, so instead, if we scatter a load of points, then we have a lot more points to store information on, and then the interpolation is a lot less. Also here we're scattering without relax, so even when it does need to interpolate across a larger gap, it doesn't look so blocky because you don't really notice the grid pattern. And if this wasn't enough, we could even just increase the number of points that we're scattering, and then, you know, it would get rid of that problem. So let me show you just, okay, well, let's look in here. So what I'm doing here, I'm grabbing essentially points on this side. So here I'm randomly sorting my point number, and then just basically keeping a certain number of points, so 5 points, but 1 per frame on between these 2 frame ranges. So essentially just going, as I scroll through, I got 1 point, and then swaps to another point, and then another point. These are just my sort of my propagation generation points. I'm going to be transferring data from those points onto this whole grid of points like this. You'll see there that's transferring some data, okay. So this, I'm creating a decay attribute from that. But because we're going to be running through a solver, we don't need to keep the points or move them with. We just need to have it generate on that 1 frame, because the solver is going to keep that data and it's going to start spreading it. All right. So in fact, currently my points do live for several frames and it just keeps switching. But even if they just only appeared for 1 frame on certain frames, then it would transfer that data and then start spreading from these points. Okay. So in here, I'm just using a near point function because I just want to know within a certain radius where is the nearest point, and I know I'm only feeding at 1 single point anyway. Okay, so we don't need to do a complex PC lookup here, just a standard, okay, where is that point? And then inside of here, I'm creating a lot of different noises. Okay, and I'm doing this just because you guys really should layer up your noises. It becomes very obvious when you just use like a standard sort of anti-alias noise or a Voronoi noise. Everything just, you can see it a mile away. So layering it up to get much more dynamic noises at different frequencies, and you can layer it in different ways. Sometimes you want to add them together, multiply them by one another, take the maximum of a whole bunch of them. Then maybe you have another one that you multiply by. If you just spend some time layering your noise, you're going to get much more natural results, and that's what we're after. So here we're taking the maximum of this variety of noises, and then I'm just fitting it to make sure that I don't get any values that are all the way 0. Okay, and the reason for that is because what we're creating here is what I'm calling a decay fidelity map, okay, or an attribute. Essentially, this is how we're getting it to spread non-linearly, so it's not spreading in a perfect circle from this point outwards in all directions evenly. We're going to be using this, checking this attribute that we've got here, so this noisy value somewhere between 0.2 and 1, where any of these points that have a fidelity value of 1 will spread this decay attribute perfectly. It'll just, if it's got any near it, it will take 100% of it and just spread it perfectly. But the closer towards 0 that we get, the less of that attribute it transfers to itself. So it spreads a lot slower. That's why I don't want any values that go to 0, because if we do have 0, then we will have 0 spreading in that area. So we'll have a chunk or like a patch in this noise where nothing spreads. Okay. Obviously, with noise, a lot of the time you don't end up with values that are exactly 0, but also it becomes difficult when your noise range is not exactly 0 to 1. So if it goes into the negative and then we're fitting this way, you can often end up with patches that do have a 0 value. So, which may be what you want. Sometimes you actually do want stuff to spread, but not spread perfectly. You actually want some areas that are left untouched. But in this case, I do want to spread the full value across the flag, but just at a different speed, depending on the noise, the patchiness of the noise. So we've got a 0.2 as the minimum, and then 1. Okay, and then I'm even just adding some additional turbulent noise on top of that. So you see, like I said, you can layer up multiple noises just to get different effects. Then clamping it to make sure that my values are strictly between 0 and 1. And then once it's between 0 and 1, if I take the power, and I'm going to recommend to you guys, look into using power as often as you can. I use it in VOPs, I use it in wrangles. In nature, almost no values are linear. Almost nothing goes from 0 to 1. Even when something is fading in, it fades either slower and then suddenly ramps up, or it very quickly sort of fades in, but then toward the end it almost slows down the fade to get to that 100% mark. Everything is sort of at least to the power of 2 or 3. Very few things in nature are linear. So if you have linear values, it's often noticeable, even subliminally. You'll watch an effect and you'll go, why is that? Something doesn't feel right. It just feels too CG. That's probably because you're not using exponential values. Okay, so here's where the real heart of this lies, is inside of this solver. So I hope you guys have used a SOP solver before. If you haven't, it's essentially basically it's running frame by frame and maintaining data from the previous frame. So when we dive inside, very much like a DOP, we have this these 4 inputs, which are our 4 inputs here, and then we have the special input, which is actually the previous frame of the result. So wherever this display and render flag is, but last frame's version of it. Okay, and then what we can do inside of here is we're making sure to maintain the data so it never goes back. So even as that point moves here, this will maintain that data. And in order to do that, we're going to use a maximum. So we're taking decay on this current frame, so that has some decay values. These all have 0, that has 1. And then we're checking it based on the decay value of the previous frame and taking the maximum. So what that means is that when this point moves to here, if we didn't do this, we would lose that value. So the same that is happening here, you'll see we've got values here. As we move, those values have moved to here, but they have disappeared from here. Instead, with our solver, if we compare our previous frame to our current frame and take the maximum, then as this moves, So let's find out which frame it moves on. Right, so let me just go back. So from frame 20 to frame 21, that point moves. But when it moves, it's saying, okay, this value now is 0. But on the previous frame, it was 1. So I'm going to set decay to be equal to 1, because the maximum, which one of these is higher? The previous frame, 1, this is 0. So I'll set it to be 1. In this way, it means that that value persists. So as we scroll forward, you're going to see as each dot appears, they all stay. Okay, so that's step 1 of this, but then step 2 is actually creating the propagation. And I'm going to use a PC open for the propagation. So we're PC opening, but we're opening to ourself, our same own geometry, because we're just wanting to spread. So we want every point to look essentially at its neighbors. But remember, we can't use neighbors because these points are not connected by lines. So we have to do a PC open to open up into this point cloud and look for your essential, like sort of spatial neighbors. So we're looking within a certain radius for a certain maximum number of points to create this handle. And then I'm initializing a max decay value of 0, because then I'm wanting to, instead of doing a PC filter here, I don't want to just filter values based on their, like a weighted based on distance. I want to actually just search every point. I wanted to search a certain radius for 10 points and find whichever one of them has the maximum decay value. I don't care how far away it is. I just want the maximum value that I can possibly find. So in order to do a maximum, I'm creating this value, and then we're PC iterating in a while loop. Okay, I've shown you guys how to do this. And then I'm creating a decay attribute where we're going to be storing the PC import. So we don't need to initialize it with an actual initial value. We just need to create the initial variable. A PC import into that handle, searching for the decay attribute, and then writing it into this decay variable. Then I'm setting my max decay to be equal to its current value, which on the first iteration is 0, but it won't be in future. And then this new decay value that we found. So if we found any decay values here, then this will be, 1, let's say. And then max decay will be 0, so it's going to be setting max decay to be equal to 1. Now the next time it loops, max decay is already equal to 1. So then it searches for decay values, and then will return 1, and so on, and it loops through those 10 points. So now at the end, we know that the maximum value within our radius is a value of 1. And this will, because we're PC opening to ourselves, will find its own attributes. So if it is the point that we're looking at has the highest decay value of all of its neighbors, then its own value will be the max decay value, which is correct. That's what we want. Then what we're going to do is we're going to use that value, and we're lerping. So we're doing a linear interpolation between the current stored decay value. So that's what we calculated in this first wrangle and set. Okay, so in other words, the value that you're seeing on these points. We're taking that value and we're interpolating between it and the maximum decay, which again, if its own value was the maximum of all of its neighbors, it's going to try and linearly interpolate from its own value to its own value. In other words, it's going to do nothing. But if one of its neighbors has a value that is higher than it, then it's going to try and get closer to that value. How much closer is it going to get is determined by this value. Closer to 0 this is, the more of its own value it's going to keep. The closer to 1 it is, the more of this new value it's going to take. Okay, so let's say our old value was 0.5. We search in our radius, we find a value near us that is 1. Then we look at this decay fidelity. So remember that map that we set using noise, we have now decay fidelity is controlling the linear interpolation between these two. So if that noise value, we're in a patch that has a value of 1, then we're going to be just taking our maximum decay, which is exactly what I said earlier. We're just taking the value as is, pure and simple, the maximum value we can find. But the closer to 0 this gets, the more likely that point is to keep its own value for longer, right? So if this was 0.2, so that very slow area, so slow in terms of how fast it spreads, will be close to 0.2. So then we're going to take, if this value was from 0 and this is to 1, so in other words, let's say this was 0.5, our current decay value is 0.5, and our max decay is 1, then 0.2 is going to be somewhere like, I think maybe 0.6 or something like that, or 0.55 or whatever, I don't know. And that will be the new value. So it has taken on, because this is not 0, as long as decay fidelity is not 0, it will move closer towards the maximum decay value, but just slightly. Or if this value is very close to 1, then it's going to take all of it. Okay, so I hope you guys are understanding that. If you are, then I know that's a bit of a boring explanation, but if you're not following, I'm trying to make sure that I explain it in a million different ways so you understand the logic behind it. Because it's that type of logic that you're going to use in Vex a lot. And if you're not quite following a system, the best way you can do it, sort of understand it, is to really logically break down each step of the way, assessing, okay, what if this value was that, and what if this value was that, then what would happen here? Like if I get confused in my code, I always do exactly that. In fact, I talk out loud to myself and I explain it to myself what each value is doing and where it's coming from, and then slowly but surely you sort of get to grips with the logic behind it. If you can understand the logic of it, and then you know the syntax of Vex, then that's pretty much all you need. Okay. And because this is happening in a solver, obviously that is keeping those values every frame. So now when we hit play, you'll see that it starts to spread. And it doesn't spread in a perfect circle because these patches where it seems to be, bending in slightly, it's because those areas are taking on these decay values a lot slower than the areas that seem to almost be reaching out really fast. Okay. Right. So that's the type of result we're getting, and I have taken that and cached it as well, just to sort of show. And if you wanted much more extreme, because these are not round, it's not circular from that center point, but it is sort of relatively roughly circular. If you want a much more extreme result, you can just go and increase the attenuation basically of your noise, so make sure that there's a much higher contrast between the different patches of your noise. Okay, so it's all about that fidelity map. This transferring here, this is the system that you're going to need to do the decay, but basically you're not going to touch this once it's all set up. The real trick here is going and getting your noise. That's why I've spent time layering up noise, and if you go and don't neglect this step is what I'm trying to say. Okay, so here we have this decay map, and we've got our moving cloth. And when I scattered here, it's a step that I just didn't mention, but under the output attributes, I've ticked this on. So I have stored my source prim and my source prim UV. And if you guys remember from last week's practical, so you should be familiar with this technique. If you're not, I'm happy to explain it, but there are a lot of resources. There's a good example file that shows exactly how to do this. This is a technique that you will use all the time, is interpolating static points onto geometry that has a matching source. So these points were scattered onto that before it moved, or a time shifted version. So we're now just interpolating those on here. And then I'm going to show you in here. So let's just talk about how to apply this data, because we have this on a bunch of points, but we want to render our cloth. So we need to access that attribute, and one of the simple ways of doing it is just transferring the attributes. Now, Don't use an attribute transfer. That's cheating. You guys know how to use Vex now, and it is much, much lighter to use a PC open. So please use it, okay? But this here has a drawback. And that's why I've got this poly reduce, is I want to show you. If we reduce this, then you're going to see we've kind of lost the integrity of the attribute. I mean, it's kind of there. It's sort of the same. You know, there's a patch of blue here, so then when we reduce, there's a patch of blue there. But basically, the geometry is storing this data that we're transferring to it. Therefore, if the geometry is poly reduced, which sometimes it will need to be, then our data is changing. You know, like the resolution of our actual map is changing. It doesn't matter how many points we've got scattered here, we lose it all by poly reducing. Okay, so I want to show you a much better way of getting this across. Okay, so let's look through our camera. Let me just pick a good frame where we can see this, and I've got a render set up. So I've got a shader, a camera, and just some basic lights. Okay, and I've applied the shader to this material. So nothing else special, just that. Okay, and in our shader, right, I've just got a principled shader, and I'm writing this to the base color. So very, very, very basic. Okay, very simple. And I've just got two colors, blue and red, in a color mix, but I'm using a bias to mix between these two. Now, if we just use this decay attribute, so this would be the equivalent of essentially reading in this decay attribute that we've transferred to the points. And if we render it, so let's just render and see what we get out of there. And what you're going to find is that, I mean, with this large amount of geometry that we have on here, I mean, in fact, this isn't even that much geometry, but with what we have, this should be fine. And we'll get a relatively similar result in here to what we would get if we do the other method, which I'm going to show you just now. Okay, so let's, in fact, let's switch this off and just let it. So you'll see here, this is kind of the result we're getting. And please, guys, sorry for the very slow rendering. I'm on a laptop here, so you know, it's trying really hard. Anyway, so that's kind of the result we're getting. But remember, if we poly reduce, then this is what we're going to get. Okay, which is not very good. You see the interpolation that's happening between the points. You can just see this kind of linear fall off, and you can even start seeing these weird grid lines and things that are happening. Okay, it's just awful. This is not what we want. Okay, so let's stop that. I'm just taking snaps along the way so we can compare these two. Okay, very drastic difference between those two. Now I'm going to switch the poly reduce off, but I'll show you here. I've cached out these points, but the animated version. Okay, so these points are in the right position, and I've cached them out. And instead, what I'm going to do inside my shader is run a PC open. So you see how we can run Vex, or in this case it's VOP nodes, but you could do the same thing with you get a Vex snippet in here, so you could do it in the Vex snippet, or like a CVEX shader. Like there's lots of different ways you can do it, but you can essentially run a PC open, which is exactly the same as we've been doing, and there's a PC filter. So same as the Wrangle nodes, like the expressions we've been learning. These are just nodes that do the equivalent. So we're PC opening, and there's our position channel, which we normally give it P, and then we feed it V at P in here. So the query position, which is what we're doing. We're just making sure that because we're in a shader, we're transforming from current to world space, taking our point position. Here's our search radius, our maximum number of points. And all of these things to do with the normal channel and the normal query are optional in the PC open expression in the Wrangles as well. So this is exactly the same. But instead of pointing to a particular file, so like input 0, input 1, because we're in a shader, we don't have that. We're pointing to a file on disk. So we're looking exactly at that decay map which we wrote out, which basically means that not the points of the geometry, but actually each pixel that is trying to render is going to run a PC open. So it's going to look for the nearest 10 points to itself, grab that value and render there. So we are essentially controlling the interpolation between the geometry. And then we are using that handle, but we're doing a PC filter for decay. Okay, so now we use this value instead of decay. Let's render and have a look at how this comes out. Wow, this is slow. Again, I apologize for this, guys. I mean, I'm sure some of you are working on slow machines as well, so I'm sure you understand it. Just becomes very difficult when you're working at a studio to go and use their monster machines that are highly optimized and a render farm that renders things in like 2 seconds flat, and then you come home to a laptop that takes 10 years to render a couple of frames. Anyway, so here we have, I remember this is our high-res geometry, but we're reading in that point cloud now. So let's compare. See here, this was high-res geometry, but just using the actual geometry itself. This is using the point cloud. And you see how we already have more detailed resolution to the edge of that. Okay, we would not be able to get that in here with this resolution unless we subdivided this like crazy. And even then, you're still confined to a grid shape unless you remesh into triangles, and that just starts getting messier as well. So you see these lovely details that we're getting. Okay, and if we wanted even more detail, we would just need more points to be scattered, which is a lot lighter than having more geometry because of the vertex attributes, primitive attributes, etc. So this is what we're getting out of this. Now let's go and poly reduce this. So now we're going to see what it looks like on the low res geometry, but we're still using our PC lookup inside of our shader. Okay. So let's see when this eventually gets started. Wow, okay. And look at that. Now this, don't forget, we're looking at the results on that poly reduced super low resolution mesh. Okay, I'll show you. You can even see that here when you look at the speck over here and the sort of folded areas. You'll see that it's that really terrible, you know, there you can see that line. This is that poly reduced terrible low res mesh. But look at the resolution we're getting on this attribute, almost identical to the previous one on the high res. Okay, this is very important to know. Using PC opens, we use it for things like wet maps and a lot of attributes that we want to transfer for AOVs, for doing, using in comp. A PC lookup is just super powerful in this context. Okay, so I hope this has taught you guys some new things and a sort of a practical way of how to apply everything we learned in the week. And hopefully because of that, everything that we learned will start to make more sense and really sink in. So like I said, please try and rebuild this setup before you just copy and open up my scene. And as an additional step, as an assignment for next week, I'd like you guys to just use some propagation like this, but to drive some other simulation. Take something like in rigid bodies and have something crumble based on the propagation, or have some grains that sort of are really sticky and wet and stick together, and then they dry based on a decay map, or I don't know. Let's think. What else can we do? Maybe something in control viscosity in flip fluid or whatever. That'll be interesting because you're not spreading across just flat geometry, but maybe like an actual 3D grid. Try to take some kind of simulation and then use this propagation technique to get really interesting results. Have it drive some kind of attribute inside of that simulation, right? Make sure, obviously, a hint with that is that if you're going to be going into a simulation, you're going to need to do this whole calculation and then do this attribute interpolate before the sim. So you're going to transfer the data over here and then make sure that inside of the DOP that you're updating that data on every frame. Otherwise, if it's reading only on one frame, it's not going to change. It doesn't matter if it's changing outside, it's not going to change inside your DOP. So you need to either use a geometry wrangle inside here to update that information manually, or certain objects will allow you to actually update, like a RBD sim. The RBD pact here has this overwrite attributes, and you can use this to update an attribute. So you could have a custom attribute, whatever you want to call it, and have it be updated on every frame. So there's lots of ways of doing it, but try to take any simulation you want, but use this propagation, and let's see what cool results we can get, because you get really fantastic things happening using this. Okay. And then I would also encourage you, within doing that, is when you're looking at your noise, and I said this is where you should really spend the majority of your time working on, is this noise, is try to actually create an area of it which is 100% restricted, so there's no spreading. But maybe you want some control over where that area is, so you don't want to just take your noise and fit this to a 0 to 1, because then you end up with these dead spots where you don't want them. I would recommend creating a separate attribute, a restrict attribute or something like that, where you can maybe paint or scatter a few points and attribute interpolate, or PC open into those points to sort of transfer this restriction attribute. And then the restriction attribute will kind of give you null areas inside of your fidelity map, which means that as it spreads, no matter how far it spreads, it will never enter maybe a certain patch. Okay. That can be very useful for something like if we were going to use this propagation as a way of burning up this flag, we would want to then maybe restrict it from ever reaching the rim so that it doesn't actually tear away and fall. I mean, maybe that's what you want, but it'd be kind of cool if this was a flag on a flagpole or something and we were burning it, that it would burn from the bottom up, but we would still end up with those sort of tattered remains along the edge of the flagpole. So in order to do that, we'd maybe have a restrict attribute to the top. So that's your assignment. Is just do some kind of simulation with propagation and then try to use like a dead zone or a restriction attribute, whatever you want to call it. Okay, I hope that's helped and that this isn't too confusing. If it is, you're welcome to ask any questions or work through this setup. This should teach you a lot, and hopefully then all of the sort of theoretical work that we've done throughout the week will now make a lot more sense. Right, so I look forward to seeing you guys next week for some more advanced VEX, and then we're going to do really quite a cool practical example at the end of that week just to see how much you guys have learned up to this point. Okay, enjoy, and I'll see you guys soon.